Okay. Anubhab and I will give you an overview of our package for probabilistic forecast reconciliation. That's called bayesRecon. This is our new logo. It's a very recent one. We still have to put it on digital. Our package is quite recent. We first released on CRAN in 2023, less than 2 years ago. And very recently, Anubhab with his supervisor, Lorenzo Zambon, they translated into Python. So now it's available in both R and Python. And the two packages share same functionalities. Also, the usage is very similar. In this talk, we will give first an overview of probabilistic forecast reconciliation, and then we will show you some examples of how to use our package. So apart from us, the other contributors are Save Simonti, Giorgio Corani, Nicola Rubato, and as I said, Lorenzo Zambon. So the framework is completely probabilistic. So the base forecast for time t plus h given observations at time t are not given by a single value on forecast, but they're given by a forecast probability distribution that can be either a parametric distributions like a Gaussian, from which you can take quantities or whatever you're interested in. It can also be specified by samples. So the forecast distribution is described by n samples. So Daniele already told you about reconciliation. So I will do just a quick recap. So we're talking about hierarchical time series that are just a set of time series that follows some linear constraints, some summing constraints in particular. But so of course, this is a particular case where the structure is strictly hierarchical. But of course, we can have more complex structures like group time series and also even more generally linearly constrained time series. But actually, our package deals with the hierarchical time series and also group time series with linearly constrained. That is something that we still have to work on. So we have a set of bottom time series that are the most segregated ones, and then we have a set of upper time series that can be computed just by summing the bottom series. And then we can also define the coherent subspace, that is the set of all the vectors that satisfy constraints. So for example, in this case, it is a set of all the points in R7 that satisfy Z equal A plus B and so on. And of course, we would like our base forecast, our forecast distribution to give a positive probability only to this kind of points, right? The coherent ones. But the problem is that the base forecasts are not coherent. So they give positive probability also to region of points that are outside this subspace S. Another way of looking at it is to look at the joint samples for all the series in the hierarchy. So this could be joint samples from the base forecast, and we see that each of these samples represents a point in the space that is not an S. So for example, for I equal to 1, the first sample, we have that 8 is not the sum of 3 plus 4, right? So this point is not on S. So this is the aim of probabilistic forecast reconciliation, to obtain a reconciled distribution that is coherent, and to obtain it from the base forecast distribution that is not coherent. So what we want to obtain are samples, reconciled samples that satisfy the hierarchical constraint. So for example, here 8 is equal to 3 plus 5, and 3 is equal to 1 plus 2, and so on. Okay, so each of these samples satisfy the constraints. So each of these samples corresponds to a point on the subspace S. So our reconciled distribution is defined only over the subset class. And okay, there are a lot of different approaches to probabilistic reconciliation. The one we follow in our package is the one based on condition. I will not give you too many details on reconciliation by conditioning, but the key idea is just that we take our distribution that is incoherent and we condition on the hierarchical constraints. I would say the major advantage of this approach is that it is well defined for both continuous and discrete distributions. And the very special case is the Gaussian case. So if we have the base forecasts that are jointly Gaussian, this is a common assumption when we have like smooth term series. Well, then in this case, the reconciliation can be done in closed form, and we obtain the same exact formulas of mean. But of course, in general, we do not obtain a reconciled distribution that is of some parametric known form. So we need to use some sampling approach. And now Anubhab will talk to you about the type.
Thank you, Lorenzo. So first, we can have a look at the different kinds of inputs and the outputs that we get when you use the different reconciliation functions that we have. So for example, in the input, you can pass them as PMFs. You can pass them as distribution functions. You can, of course, pass them as samples and as the Gaussian mean or Gaussian covariance matrix when you're using the Gaussian reconciliation. The major advantage that comes with, I'll show it later with the discrete case, is that in the output we have the parametric output, the PMF or the samples, and that's also user defined. But the advantage is with the PMF, because what I mean by PMF is that it stores the results as PMFs on the non-negative support. So you don't take a lot of space when you're storing it in this way. So it's memory efficient. Okay, now I move on to the first case, which is the Gaussian case. It's, as Lorenzo said, it's the same as mean T, the solution. And for the input, you need to put the aggregation matrix A, and you need to pass the mean and the covariance matrix of the Gaussian distribution that you have for the base forecast. As the output, you get, so this is the Python version. Here it comes as a dictionary, and you need to get the bottom reconciled mean and covariance. And you can pre-multiply them mean with the, let's say, the matrix A, and you can get the same for the upper. And you can also do a sampling based on this Gaussian and then multiply that with the A matrix to get the uppers. And since it's Gaussian, it works that way. Okay, so a Python example is about the infant mortality dataset that we had, and it's disaggregated in two ways. So it's not hierarchical, it's a group time series. So you can disaggregate by the states and also by gender. And this is the structure. So we did the Gaussian reconciliation for this dataset. And so you just need to pass them, as I said, the matrix A, the mean, and the covariance of the base forecast. And you get the reconciled distribution like this as dictionaries, and then you multiply them with A. And you obtain the mean and the covariance for the uppers. And these are the point forecasts, so the means, and you can see that the male and the female, you add them up and you get a reconciled version as the total for each state, and also the grand total. So you get reconciled forecasts by doing this. Okay, so the next case would be a non-Gaussian case, and Lorenzo would be described.
Yeah, so as I said, when you are not in the Gaussian case, you need to sample from the reconciled distribution. And in Bayes, in the bayesRecon package, we have implemented the bottom-up importance sampling algorithm. There's an efficient sampling algorithm based on importance sampling. It works with both continuous and discrete distributions. It works with both strictly hierarchical but also group time series. The main limitation, I would say, is that it assumes conditional independence between forecasts of the different series. This is actually a strong limitation. We will probably work on that. The input of the functions, first of all, the aggregation matrix that describes the hierarchical structure. Then the base forecast, that is list of length and the number of series. Each item of the list is either the parameters of the forecast distribution, in the parametric case, or the vector of samples. Because I forgot to mention that the Bayes algorithm also works with samples as the input. And then we also need to specify in the parametric case which distribution we're using, like Poisson and binomial, whatever. And also if the samples we're passing are continuous or discrete. And then as output, we get samples from the reconciled distribution. So we can also specify the number of samples that we want. So, okay, let's see an example. This is a new dataset we have made available in our package. We made available both the data and the base forecast. So the data refer to counts of extreme market events in 5 different economic sectors like finance, energy, so on, together with the total. And these are daily time series. They cover about 13 years of trading days. While the base forecasts were produced using a spread-driven model, they're one step ahead forecast, and they are parametric. The parametric form, so that they're negative binomial distributed. So, okay, let's see some code. This is our code. Okay, so we just pick an example for one trading day. We build the aggregation matrix. In this case, simple is just one row matrix. We have to build the base forecast, which is a list of length n, in this case 6. Each element of the list is a list with the parameters of the negative binomial distribution. So we specify the size and the mean move. And then we can run our reconcilation function. So we specify parametric distribution, negative binomial, and we ask for 10,000 samples. And we see that it is pretty immediate. So then we can get the samples, reconciled samples. It's a matrix with n rows and number of samples columns. And if we look at the free samples, we see that they are coherent because all is equal to the sum of all the others. And okay, I would like to show you also another example using this algorithm, this function, but in the temporal framework. So we are doing temporal reconciliation using Bayes. This is a series taken from the alpha dataset. So the daily sales from a Walmart store of a single item. And we can aggregate it to, for example, weekly, 2 weekly, and 4 weekly series. There is a function in bayesRecon to do that. So we just specify the aggregation levels and we get a list of series. And okay, we just compute the base forecast using the smooth package. So for example, we take the bottom series, that is the daily series. We specify a gamma distribution. We forecast 28 days ahead, and we ask for samples. Okay, so we then run samples because we know that it's a count series, and we collect all the samples in a matrix the dimension is 35, which is the dimension of the hierarchy, temporal hierarchy, times the number of samples. And okay, so we can now reconcile our Bayes forecast. So first of all, we have to build the regression matrix. There is for temporal hierarchies, there is a function. So we just need to specify the aggregation levels and the number of steps ahead of the most disaggregated series, and the function builds the aggregation matrix A. We have to transform the Bayes forecast into a list of vectors, because it was a matrix. We transform it into a list of length n of vectors, with each vector is the samples for that series. And then we run the recurrent Bayes function. So we just pass the Bayes forecast, we specify the samples and the discrete. And also in this case, we see that it's very, very fast. And yeah, just a plot of the forecast, the Bayes forecast and the reconciled. So now Anubhab will show you another example.
Yes. So there could be another case where you have the bottoms which are discrete, and it could be a very large hierarchy. So the number of bottoms are quite big. And what you observe in that case is, as you go up the hierarchy, the series, they tend to look continuous. So we call this the mixed case, which is with discrete bottoms and continuous uppers. And we have two reconciling functions that we can use in this scenario. And both the functions, they have the same input and output structure. It just depends on you, which one do you want to use. And I mean, there's a bit of trick to that, which I'll tell later. Okay, so the input, you need the aggregation matrix, and the FC bottom, it's the bottom Bayes forecast, the FC upper, the upper Bayes forecasts. And since the uppers are continuous in this case, we consider them to be Gaussians. So you need to pass them like FC upper mu and FC upper sigma as the mean and the covariance metrics of the Gaussian. And then there is the bottom type, which could be params, PMF, or samples. So you can pass parameters of distribution. You can pass the PMF, which was the case I was talking about before. So it's a PMF on the non-negative support of integers, or you can pass samples. And when you have the bottom in type params, you need to specify the distribution that you're doing. It could be negative binomial, it could be Poisson. You need to specify that. And as return type, you can opt for getting a PMF as the output, because I mean, you are considering the uppers to be continuous, but they are actually not continuous. They are still integers. So as output, you get the PMFs for the whole hierarchy, or you can opt for samples, or both as you want. And yeah, we show this with the M5 example. I mean, it's a huge data set. So we just took the one store, and the hierarchy looks like this. So you have the daily time series of the sales from this particular store, and it could be categorized into hobbies or kind of food or household items. And it's a 3-level hierarchy that you can see here. And yeah, so for the Bayes forecast, as I said, because it's a little tricky for the upper, you need to pass them as this sigma and mu when you're passing the FC upper. And for bottom here, we pass them as PMFs, like we said, on the non-negative integer support. And we do the reconciliation. So yeah, this is example of one of the bottoms, which is a PMF. And you can see that as you go up the hierarchy, they look quite continuous. And here I would say also looks pretty much Gaussian to me. And there are some outliers maybe, but it's not important. So the considerations are okay with the implementation that we have in mind. All right, so the first method is the mixed conditioning. And for Bayes forecast, this is stored in our package, originally obtained in the R package by Lorenzo and Dario. And yeah, so we have the same one in Python now. So you need to call the mixed cont function if you want to do this reconciliation. And yeah, you pass them, as I was talking about before, the input. And you can also set the seed if you want. And then you obtain the output, which again comes as a dictionary in Python. And yeah, you can obtain them as PMFs, as I was talking about. And you can see that, the computation time, I mean, we had like 3049 bottoms. It's quite fast. It takes around 18 seconds to run. Okay, and then we have the second method, which is the top-down conditioning. And since both the functions, you can see it's the same input that they have. So you just pass the same inputs and you do the top-down conditioning. And in this case as well, you can see the reconciliation is quite fast in 23 seconds. Now, the question about which one to use, I would say if it's not a very big hierarchy, you can stick with the mixed conditioning, or you can even do top-down. It doesn't really matter. But if you have a very large hierarchy, then we have seen that the top-down conditioning, it works more efficiently and it's more accurate. So yeah, if you have a large hierarchy, you should probably consider doing the top-down condition. Okay, so for some concluding remarks, our package is fully probabilistic because we always get a reconciled distribution, either in form of samples or in form of PMF or in form of parameters of distribution. Yeah, and it works well with all the cases. So it works with continuous data, with discrete data, or if you have a mixed hierarchy. And it's quite fast, as we saw with the top-down conditioning and the mixed conditioning, that even for large hierarchies, it doesn't really take a lot of time, both in R and Python. Yeah, this is the initial version. Actually, for Python, I made a second version, which also has now the Minty and the orthogonal projection, but it's very basic. Yeah. And yeah, this is an active research project in GitHub. And if you want to collaborate, it would be really good for us, because particularly what I saw is when so I work in a department which works with sustainable energy, and we have data like daily data. And for that, I saw that if there is no way to produce base forecasts from my package, it could take a lot of time to just get the base forecasts ready for reconciliation. And that would be something that could be really helpful, that if the package is able to produce the base forecasts while doing the reconciliation. So yeah, and also I will include nonlinear reconciliation methods for the package, which I would be giving a talk about in the ISF conference. I have some methods for nonlinear reconciliation, and I'm pretty sure we can collaborate later for the R version as well to make them available. And these are the QR codes for the packages. If you want, you can scan them and have a look. And yeah, thank you for this.
Thanks very much for your presentation. I would guess with all the reconciliation people in the room, there are lots of questions. No? Yeah.
Yeah, so thank you. This was really interesting work. I'm curious about the mixed case when you've got continuous at the top. What are you doing? Do you RAM the results, or because when you come to reconcile, you want to make, they all have to eventually be discrete?
I think Lorenzo would be the best person to answer this, because he's the one that came up with the methods.
Yeah, so yeah, you're right. Of course, so they are continuous in the sense that you typically assume Gaussianity, but then in practice you have to round the. In practice, what we do with the top-down conditioning method is that we round the samples and then we to integers, and then we do the top-down. While if you are using the use conditioning instead, you actually don't need to do any rounding, because you're doing importance sampling. So you're just evaluating a density at discrete points. That isn't the problem.
Okay, so you basically take the Gaussian and you take the discrete part of the Gaussian.
Yeah.
Turn it into a P.
So yeah, in mixed conditioning, you just evaluate Gaussian density at discrete points. But in the other case, you have to round. And the output, of course, is script here, because then you obtain discrete bottom samples, and if you sum them, they remain discrete.
Have you thought about making it more general so you can do the constraint matrix like Daniela was talking about?
Okay, so for the top-down conditioning method, it's pretty hard, I would say. So now it doesn't work with group n series right now. It just works with strictly hierarchical series, because you really need the hierarchy to do the top-down. Also, it has some kind of restrictive assumptions, because we assume all the bottom to be discrete and like all the upper to be continuous. But of course, there could be mixed cases with some of the bottom are smooth or some of the upper straight. So there is a lot of work still to be done. Probably the mixed conditioning would be easier to generalize, but it has the problem that it is basically an important sampling. So when the dimension grows, the effective sample size decays exponentially. So even with a few hundred series, then it's really difficult to make it work.
So regarding this problem of constraint or hierarchical, so just think about a hierarchical case where you have your hierarchy of upper and bottom series. You know that you have a hierarchy, you choose what is upper, you choose what is bottom. You can also change the constraint, and one upper can count. So if I do this with whatever the mix, the results are changing. So if I change upper and bottom, I mix the rival. So I take some upper and take some bottom, and some bottom can. So I can construct also a hierarchy in this case. So it's still in your framework, but the final result is the same or is it changed?
Good point. I answer this. So in principle, yes, it should be the same results. I think the current implementation assumes that correlation matrix is just made of 1 and zeros. So it will not work if you try it right now, but I think it would be like a minor change. Because in principle, the method works with any linear constraints, with any matrix, but right now it doesn't. But yeah, this is a really good point. We should do that definitely.
I think I mix the mixed condition and the top down.
With the top down conditioning, you need that the constraints are summing the strengths. Yeah, you need it because
Yeah.
Thank you.
What differences did you find when designing the R and the Python versions of the packages? Did you feel like to make it work well within each ecosystem, you had to make some changes?
At one point of time, I thought that I would need to make some changes because with the top-down conditioning specifically, it was not working out so well in Python. And then I asked Lorenzo about I asked him quite a lot of times that how exactly did you do the sampling procedure when you were doing the top-down? And when he explained that part to me step by step, I was like, okay, let's get to the bottom of this. And finally, it worked out to be the same. And in the end, it worked out. And the results are the same with both. And even the sampling algorithms, they are the same.
So, nice. And I understand Python was written after the R version?
Yes.
Did you learn anything about the R version when trying to recreate the Python one that maybe the R version could be improved upon, or there were some mistakes of the past?
I think, yes, I had one or two suggestions that I told to Lorenzo and Dario, and they said that, yes, this could be a problem. So there was something related to the order of the base forecasts, and but it eventually worked out, and it works.
Yeah, you definitely spotted
why. Yes.
That's for sure.
And so maybe coming back to what you said earlier about the sports stick hierarchy. So how does it work for temporal? For example, if you have 2 years of data and you only want to reconcile like on the yearly level, those are two strict hierarchies, but like they don't have a joint top level. Was that still?
Oh, okay. Yeah, it's not a problem, I would say. So if we go back to this case, so here when you specify the aggregation letters for the aggregation matrix A, you specify both the aggregation letters and the number of steps ahead. So in your case, we could say that H is equal to 56. So to be not for 8 weeks ahead. So in that case, we wouldn't have a top series. We would have like two top series. Two top series. I mean, one top series, but two top forecasts, and it would work the same. Also, so in this case, the hierarchy is well, strictly hierarchical, but we could also specify like cross ladders. So we could put 10 here. So in that case, it becomes a grouped hierarchy, and still it works.
Yeah. So it doesn't have to be like a common divisor.
Yeah, exactly.
Nice. I guess you also have the problem that we're facing in the hierarchical forecast that like ideally you want to specify month instead of 28 days, right? So because like businesses have like monthly forecasts for January, February, and then everything becomes super messy. At least like, so I don't know if you're trying to solve that problem already.
I haven't. No, but it's a very good point. So yeah, we actually not. We haven't dealt with that problem yet.
Actually, I don't know if you also try to work on that.
Which was it then?
Yeah, so with temporal reconciliation, for example, if you try to reduce how they forecast into monthly,
Yes.
they
Got
can
it.
actually say 30 days, but that's not a month.
I was thinking of that as my other question as well. I don't think I've seen anyone try to do irregular temporal reconciliation.
Yeah.
Like you've got a leap year, for example, you've got your daily data here. How would you do your annual aggregate? I think the hardest part here is the data structure, because the matrices here, you've got a functional aggregation problem for that irregularity. I think it's really hard to represent in any way, full stop. And I'm thinking about it quite a while, and I don't have all the answers yet.
And even another problem is when you have like an integer number of weeks in the year, so you have to deal with.
Yeah, it's the same problem for that.
Yeah, thanks. I also can figure it out. Yeah, I try to implement it, but it's not. It becomes super messy. So if you want to find out, I'll be happy to know. But one thing I was also thinking, probably the Gaussian case is like the fastest, I assume, rather than the sampling. So maybe the question is about sort of scaling or efficiency. Like what makes the method in the end slow? Like what drives the complexity of each method?
You can also put it boxing. I think because in the Gaussian case, it's analytical, so it takes very less time because you just need to, do some matrix multiplication and the analytical comment comes out. But for the other ones, you need to really like sample out of variance and distribution, and it's not as straightforward as the Gaussian case. So that's why it takes a little more time for the others than the Gaussian variant, I think. But
yes, the Gaussian case sort of in space complexity scales with the n by n, I would say, and then you then parallelize at the matrix multiplications.
Yeah, the I would say the time bottleneck here is the inversion of number of upper times number of upper matrix. So if you have a really huge hierarchy, as Anita said, we have the same problems. For the Buoy's algorithm, it's based on importance sampling. It's like a more it's based on importance sampling, but it's more efficient. I would say that the problem here is with the effective sample size. So if you have a very
Can't be too
big hierarchy, especially if you have a strict hierarchy, it's easier. If you have a group structure, then you have a kind of extra constraints apart from the hierarchical ones. And so that can be a problem. So we tried it with the hierarchies up to, I think, 100, something more serious, and it worked fine. But probably it wouldn't scale to like thousands of series. But we hadn't tried it.
I did try the electronic data set. I mean, it was a huge data set, like 4,000 of them.
Okay.
But yeah, it took a lot of time when I tried to run the buoys and also the top-down and mix it. It took quite a lot of time. I mean, I parallelized the code in Python and I tried to run, but still it took quite some time to get to the results.
Yeah. Well, I think the most efficient in the end is the top-down conditioning. That one you can use it even for us very big hierarchies with some series. But also we would like to make it even faster and like more efficient. I was also thinking about writing the core algorithm in C++ to make it faster. But yeah, right now it's able to deal with the hierarchy with the 3000 series without any problem.
What defines large time series space is around 1,000 per time series. Where it struggles, the Python understand that. Right? In real life, that we have like 200,000 Python stars, or sometimes only a diffuse time series systems. What suffices large time space for this case?
Okay, and so of course large is relative. So I was referring to 3000 series as large, but probably in real business scenarios, that's not the large hierarchy. So in that case, if you use the top-down conditioning, I think let's say this is a first implementation. It can be done more efficient.
No, I can imagine from what I see in something, it's quite. It can competition be challenging. I just would like to understand where it gets problem or computational problems.
Yeah. Just
an estimation.
Yeah, I actually don't know about the complexity. I haven't tried to estimate it. I would say it could be. So the problem here, I would say that so we store the forecast as PMFs because it's a very compact way of representing the parametric distributions of sampling instead of just samples. The problem is that when you go to the aggregated levels, then the support grows a lot. So I would say the main bottleneck is that. So it's not more than the number of series in the hierarchy, it's more like the values. So if you have very aggregated series, they probably are very big. So the support of the PMF goes from 0 to 1,000, so 10,000 and so on. Yeah, I would say that's the main bottleneck of the algorithm.
In terms of having more space complexity.
I would say more about time, but yeah, of course you're supposed to store them with PMS objects, so probably both.
You could possibly approximate those PMFs because they're going to be smooth. They're not, I mean, if you've got a PMF over 1,000 discrete values, they're going to be quite smooth functions. So you could store them efficiently if you take advantage of the smoothness.
Yeah, that's a good point. That's a good point. The point is that we in the top-down algorithm, we take a PMF and we iteratively split it in two, whose sum is the top one. And to do that, we use this sampling.
Grid search kind of thing.
Iteratively split into, and so I'm not sure if we can do that. Like, if I assume you were talking about fitting a distribution on the PMF.
No, some kind of monometric smooth curve that only takes like 10 parameters instead of 1,000 parameters, which is what you're currently using to store it.
Yeah. This is a very good point. We can think about that.
Yeah, I think also the point is that when you do the top-down, you take the sub-hierarchies and you do it explicitly for that, and then you do it for all the sub-hierarchies. So, I mean, even if it's true that it's continuous on the upper, your stage shading is like upper and bottom, even in the higher series. So maybe that also takes a little bit more time to do.
Okay. Please join me again. Thank you very much.